Okay, hello everybody. Thank you very much for joining today. As Claire has indicated, this is the first of a series of 4 training seminars. You can see the dates of the next 3. And we're going to take you on a bit of a journey. I hope many of you can join all 4. Our aim is to go through how to specify the performance of a positioning, navigation and timing system, not just in terms of accuracy, but other performance characteristics. We're then going to talk about assessing risk and frameworks on which to do that, both at a receiver level and a system level. That's in the 3rd training seminar. And then in the 4th seminar, we're going to start thinking through mitigations, just some starter thoughts on mitigations. We're hoping to be able to present some more seminars later in the year to take that a bit further, and also that they'll include case studies and so on. So welcome, and hope you can join us through each of these 4 sessions. So these are some of the questions I'm hoping to address in my introductory talk here. There are certainly multiple factors that lead to accuracy in a system. And accuracy really is not a constant in any way at all in a satellite-based navigation system. And I'm going to try and get a little bit under the skin of that. I'm also going to talk about multi-frequency and encrypted signals. And a bit of a teaser, really. I'm going to make the point that they can be a help in certain aspects, but they're rarely a solution to the resiliency challenge in their own right. And overall, if there's a takeaway that I'm aiming for from this talk, it's an awareness that receivers and systems don't always operate in exactly the same way. And having an awareness of the background to that is what I hope to get across in this talk, to allow you really to start asking yourself and maybe your suppliers some questions and start thinking things through a little bit more towards a more resilient system. So to get us going, some basics. GNSS, Global Navigation Satellite Systems. There are actually 4 of them, and roughly going from east to west to east on this slide. So the US system GPS, of course, the EU system Galileo, the Russian system GLONASS, and the Chinese system Beidou. I think that stands for North Star. Beidou, as in Beijing, capital of the North, Bay, North, Do, Star. So there are 4 GNSS systems. There are other regional systems. For example, India and Japan have got regional systems. But it is true to say there are only 4 GNSS systems, and these are they. Now, you may have seen other presentations I've done, and I've regularly come back to this chart because it is just such a good anchor chart. If there's any doubt in your mind about where the satellites are and their kind of basic motion, hopefully this chart can explain that, because it's really vital to understand those principles to begin to be able to think through how the navigation systems work and some of the issues you might face. So let me just try and orient you on this chart. I'm going to focus mostly on the vertical axis, which you can see starts just above the surface of the Earth, goes up to 5, 10, 15, 20, up to 24. So geostationary, or probably more accurately, geosynchronous orbit, is this wonderful band 36,000 kilometers above the equator, where satellites orbit at the same rotation speed as the Earth. So their period of rotation is exactly 24 hours. And therefore they stay stationary above the Earth. Mostly communication satellites, having the wonderful benefit that you can have a stationary dish on the side of your house or in your field or your on top of your building, and it'll always be pointed at the satellite. You don't have to have have a moving antenna, or an antenna that can see from multiple angles. So that's Geosynchronous Orbit, 36,000 kilometers. It's in the Clark Belt, Arthur C. Clarke, 1940s, 50s. A wonderful and crowded piece of real estate. There are some navigation assets there, but they're augmentation systems, and that's a bit outside the scope of this talk. But for example, EGNOS in Europe is an example of a system, an augmentation system, that does have a number of satellites in the geostationary or geosynchronous arc. Let's go right down towards the Earth now. You can see Iridium, Hubble, and the International Space Station there. Yeah, I mean, we're talking about orbits here just a few hundred kilometers above the surface of the Earth. 400, 500, 600, 700 kilometers. I think the Iridium constellation is about 800 kilometers above the surface of the Earth. These are called low Earth orbits. Not exactly perfect for navigation for a number of reasons, but one of the simplest, most basic reasons is that you need an awful lot of satellites to give global coverage, because they're so much closer to the Earth. The beams from them only cover a tiny fraction of the Earth's surface. So then when people were conceiving back in the, back in the 60s, 70s, I guess, the GPS, what was to become the GPS system, medium Earth orbit, was the one that was chosen. And there are an enormous number of advantages here. So we're talking about satellites which are located between 20 and maybe 23,000 kilometers. I think GLONASS is 19,000 kilometers above the surface of the Earth. And in those orbits, the period of rotation is about 12 hours. Not exactly, depends on the height and everything, but about 12 hours, so a couple of times a day. And these satellites are moving extremely fast. In round figures, about 2 miles per second to complete those orbits in that period, or 3.3 kilometers, I think it is, per second. So they really are moving very fast indeed, and we'll come back to that. Another key advantage is that with a satellite at that altitude, the footprint of the antenna from the satellite can cover the whole Earth. So you can get away with a constellation with global coverage with somewhere between 24 and 30 or 31 satellites. So this is where each of the GNSS systems have their satellites. One of the results of this is that, as you will be aware, the power levels of these satellites, by the time they reach the surface of the signals, the power level of signals by the time they reach the surface of the Earth is extremely low. And there are all sorts of comparisons to give you an idea just how low. My favorite one is like a little pocket torch, about a 1 watt torch. If you were looking at that from 700 miles away, that's approximately the power level of the signals from the GNSS satellites when they reach the surface of the Earth. I think another one is a car headlight in Australia viewed from Europe. So extremely low power level. And this diagram, I won't go into too much detail, but this is a spectrum analyzer plot. So along the horizontal axis there, it shows frequency from 10 megahertz up to 3 gigahertz. And the vertical axis is an indication of power as seen by the probe or antenna when this shot was taken. And you can see all sorts of signals within that spectrum. And this is just kind of representative of the UK. So number 10 there, for example, about 2.4 gigahertz. Those are Wi-Fi access points. So Wi-Fi has lots of different frequencies around 2.4 gigahertz. If you go to the other end, the left-hand edge of this chart, you can see number 1 and number 2. Those are digital radio and FM radio. And then many of the others, for example, sort of 3, 4, 6, etc., 8, 9, I think, are mobile telephony, so GSM, LTE, and so on. Number 7, you can just about see it in the middle there. Number 7, which is a bit lower down. Now that's iridium, just above 1.5 gigahertz in the L band. So remember how close to the surface of the Earth those iridium satellites are in low Earth orbit. And you can see how low even their signal levels are by the time they are received in this example. So where on Earth are the GNSS satellites? Well, the answer is you can't see them. You can't see the signals when you look at them using a spectrum analyzer, a signal analysis tool like this, because they're buried in the noise. So this blue band at the bottom is what we call the noise floor. And the signals, the GNSS signals, are spread out and they're below the noise floor. They're within the noise. So I really can't emphasize enough how low is low when it comes to the power level of these signals. And that's one of the sources of the vulnerabilities that Guy will talk about in his talk after me. Well, it's beyond the scope of this talk to go into detail on how a receiver works, but I want to give you a flavor for it. I'm going to try and give you a flavor for it in the next couple of charts. So the indicated here, look at the top half of the page. You can see in red, the code coming from a GPS, let's keep it simple, a GPS satellite. So digital code, 1s and 0s. So that's coming down as part of the signal from the satellites. But when it reaches the Earth, it's below the noise floor. So we've got to find a way to bring that out and align with it, find it, in other words. It's called correlation. And in simplistic terms, or simple terms, the way that that is done is that the receivers that we all have and know and carry about, including the receivers in our smartphones and cars, for example, as well as professional receivers, they all generate a local replica of this code. And in simple terms, the receiver searches for the signal until the local code is aligned with the code that it's seeing coming down from the satellites. And you can see that in the bottom half of the page. And when this happens, it's called correlation, when the code, the replica code in the receiver, is precisely time aligned with the received code from the satellites. Another view of this is shown here. So this rather complicated chart on the left here is indicating that the receiver has to search in 2 dimensions in order to find and correlate with these signals. So the 2 dimensions are frequency and effectively time. So why does it need to search in frequency if all the satellites are transmitting at the same frequency? Well, it's the good old Doppler effect. So the satellites, as they rise, come into zenith above the user and then set. And when they're rising, they're actually moving towards the user. And when they're setting, they're moving away from the user quite quickly, about 800 meters per second, in fact, towards and away from the user. So that gives you a frequency shift, a Doppler shift, just the same as an ambulance, classic example at school, an ambulance coming towards you, driving away, you hear that difference in frequency. It's exactly the same effect with the satellites moving towards and away from the user. And of course, if the user themselves is moving, that also causes a frequency shift. However, because the satellites are moving so much more quickly than most users will move, the biggest contributor is the satellite motion, which is answering one of my questions in the blackboard at the beginning. That's why GPS can work so well on a jet moving so fast, because relative to the satellites, that jet is moving rather slowly. So anyway, here you can see that little peak on the left-hand chart is the signal which has been correlated and found frequency shifted, and shifted in time. And when acquired, the receiver will move from searching for the signal to tracking it. And when it tracks the signal, it can start to download the information in the navigation message, which includes the satellite exact locations and the time of transmission and so on. So in very simple terms, that's how a receiver is doing its job. And I hope that gives you a feel for some of the dynamics. And linked to that, you'll be able to hopefully put in perspective some of the vulnerabilities that Guy and Dave will talk about later on in this session. So in order to actually get a position, which is what many people are after, or indeed a precise time, which is also what many people use GPS and other GNSS system for, you need 4 satellites. So you need to resolve for XYZ, so 3D position or latitude, longitude, height, as you wish. And the receiver clock, it's not an atomic clock, such as you've got synchronized across all the satellites. It's a local, relatively inexpensive clock. So the receiver clock has got a clock bias, an error, if you like. And that needs to be resolved as well, so that the precise position can be calculated. So baseline is you need 4 good satellites to get a good 3D position and or accurate time that's aligned or that can be calculated from the precise time in the satellites themselves. I think we're going to get a bit less technical from here, so hopefully you're still with me. So, well, here's an example of some satellites being seen and tracked. So on the left here, this is actually an Android app. If you've got an Android phone, I recommend you download it. It's called GPS Test. And if you're a GPS geek or indeed a GNSS geek, it's great. It allows you to look at which satellites you can see and also which satellites your receiver in your device is tracking. So here on the left, you can see 11 GPS satellites and 11 GLONASS satellites. You can actually see at the bottom of the screen one of these so-called space-based augmentation system satellites. That would be EGNOS. That's the geostationary satellite I was talking about at the beginning. And you can see in this example, under that C over NO column in the middle, that 2, 4, 6. So 6 satellites are being used in the position calculation. And the receiver will pick satellites that give good geometry. You don't want them all clustered together because you know, your resolution will be worse than if they're well spaced. On the right hand side, you can see a bit of a cacophony of satellites. But that is approximately how many, if each of those crosses is a satellite, that's approximately how many navigation satellites you'll have in view in a clear sky outside pretty much anywhere in the world. And in round figures, you've got 10 each visible from GPS, GLONASS, Galileo, and Beidou, plus a few augmentation satellites, and maybe these Indian and Japanese satellites and so on. So an awful lot. So there are many, many more satellites in view than you need to get a 3D position and resolve time. Just got a simple example here to illustrate that. So here I'm sticking to GPS and GLONASS. And you can see that in this example, the user was outside, and the blue lines are GPS satellites visible, so somewhere between 8 and 12. And the red line going left to right is indicative of the number of GLONASS satellites visible over time, similar number. And of course, if you add the two together, you're going to be up in the high teens. If you put that into a example use case, here you can see the blue and the green lines are using GPS only, whereas the red line is the position when using GPS and GLONASS together. And this chart just introduces the concept of why it might be better to have more satellites in a built-up area. And this, I think, is in Los Angeles. So something's going on with the blue and the green lines. And I believe it's correct to say that there are two likely sources of the worst positioning using GPS only in this example than GPS and GLONASS together. The first one is that perhaps the view of the satellites is blocked in certain areas, particularly along the top of that track in the middle there, higher buildings, and your geometry will be worse. Maybe you won't even see a good, so therefore you won't see a good spread of satellites. So that can degrade accuracy. But in addition to that, with high buildings, you're likely to get signal bounces rather than line of sight satellites into your receiving antenna. And in some cases, the receiver can measure the extra path length for the bounced signal, multipath effect. And that can give quite big errors, as you can see here. So it's not always the case that more is better in an open sky situation in a field or in an aircraft. You really don't get much advantage in accuracy by using multiple constellations. But you can do in constrained environments such as this. And I think in our last course, we'll probably touch on how multiple constellations can improve integrity of the data. So let's talk a little bit more about the sources of error. So here's an indicative diagram of the satellite in its medium Earth orbit. Signal in that sort of red color, indicatively just coming down quite happily, actually, for about 19,000 of its 20,000 or so kilometers. Nothing to worry it. But then it hits the ionosphere, the troposphere. You get delays and variable delays. I'll come back to that in a minute. And then right at the local receiver level, you might suffer multipath effects and receiver noise. So these sources of error are the principal sources of error that would lead to an inaccuracy in the reported position from a receiver. And it's quite a complex subject to go into detail, but at a very top level, the error sources are made up of a bias, which is predictable, as well as some noise effects. So the bias, for example, I'll give you a simple example of the bias. If you're looking at a satellite with a low elevation angle, the signal is going to be traveling through more ionosphere and troposphere than a signal coming to your antenna from directly above. So you can reasonably expect that the ionospheric and tropospheric effects are going to be more challenging or more impactful in a low elevation satellite than a high elevation satellite. The same is pretty much true for all of these different effects. There are those sort of biases, plus there are random error type effects. How do they all add up? Well, here are some indicative examples, and I've purposefully not put any units on the vertical axis. Because the answer to how accurate is your receiver is it depends. It depends on all these types of factors. But in terms of order of magnitude, or the direction, think of the left-hand column here as being for a single frequency, autonomous, standalone GNSS receiver. probably being 4 or 5 meters under benign conditions in an open sky. And you can see the composition, typical composition of that 4 or 5 meters. Well, the biggest bar you can see straight away is the grey one, which is the ionosphere. And then there are contributions from each of the other 5 sources, which add up to give you your sort of 4 or 5 meters. The middle column is indicative of a lot of space weather. So there are solar weather, if you like. It's very variable. So all receivers have models to back this out, but the models don't normally take account of the actual conditions at a particular time. So you can get more intense weather and effects like scintillation, for example, particularly at equatorial latitudes. And as indicated here, they can dramatically increase the grey bar, the ionospheric error. And I've shown it as approximately doubled, but it's not at all difficult to imagine it can be more than that. And then on the right-hand bar, there's an example with more benign ionosphere, but in a built-up environment with multipath. And well, that's a variable feast, but as you'll see in the next chart, or the next but one chart, multipath tends to vary with building height, and it can be a very significant source of error if uncorrected. So here's a chart which I'll just explain briefly. Along the bottom axis here, you've got the reported accuracy from a receiver. So starting on the left with 0 to 5, 10 meters, right up to 100 meters on the right. And then this is a population of 1,087 experiments. And this chart actually comes from an online GPS course, which was run by Stanford University. Frank van Diggelen, who's a fellow of the Institute, and the late Per Enge, very well worth watching. And I've put the link here if you want to follow it. If you really want to get into how a receiver works and how the constellation and receiver work in harmony, I can't recommend it highly enough. But they ran a live, crowdsourced, effectively, experiment with over 1,000 users around the world. And you can see at a glance that the blue errors are huddled over to the left, whereas the red errors spread across the chart. And red is a city-town environment, and blue is an open sky environment. So the mean error in open sky, about 5 meters. The mean error in a city and town is about 17 meters. So from what I've just said about the sources of errors, I think you now know why that is. It's mainly due, that worsening in the city-town is due to a combination of worse satellite visibility, worse geometry, and in particular, it's all very likely to be multipath effects. In fact, Frank and Per Enge went on to develop this law of urban multipath, which it kind of is about right, I think, empirically. And along the bottom axis here, you've got building heights in terms of number of floors, and the vertical axis, the mean error of the GPS reported position. And they postulated that the law of urban multipath is that the accuracy is equal to the building height plus 5. So if you're on the ground level, 5 meters, but if you're in an environment with 5-story high buildings, you can effectively double that to approximately a 10-meter accuracy if multipath is uncorrected. And I can kind of second that. I remember being in Hong Kong about 10 years ago, looking for a restaurant on the island, and I had an iPhone 4, I think 5 at the time, and the position was being reported across the harbour on the north side. So hundreds of meters of error, certainly due to multipath from the 80 story high buildings around me. Okay, just a few more here to finish off. So I did mention geometry. Yes, so geometry being the spread of satellites, if you like. And you may hear people or GPS receivers talk about Dop, dilution of precision. And that is an indication or a measure of the geometry. High Dop is bad. So high dilution of precision is bad. Low Dop is good. And typically in a city environment, you might get a Dop of about 2, 1.5, 2, maybe a bit more. And another rule of thumb is if you multiply your root sum of squares error from all those different sources, so the 5 meters I was talking about, by the Dop, say 2, that would give you a rule of thumb of the accuracy you could expect. So 5 times 2, 10 meters if your Dop is 2. So that's why, one of the reasons why when you can only see a slice of the sky, you're going to get high Dop and worse accuracy. So what can that look like in practice? Well, you've all, I'm sure, seen examples like you can see here. So here we are in a building with a flat roof. The receiver's just inside a north-facing window. It's a single frequency GPS and GLONASS receiver, so it's reasonable we can see 18 to 20 satellites. So based on what I've said, I think you can begin to hopefully really think and articulate what might be going on here. Why is the position that's being reported all over the place, as it shows in the bottom there, about 11 meters of accuracy over 3,000 fixes, so almost an hour. This is getting a fix every second. Okay, well, the answer is the Dop is poor because the visibility, the slice of the sky that can be seen through the window is not as good as an open sky. The roof of the building would be attenuating the signals. And it's very likely that there's some multipath effects going on as well. So add those together, you're going to get these types of effects. And why is it jumping around? Well, the answer, simply put, is because the satellites are not always in the same position. So, they're in different locations, and it's a very dynamic situation. So there's a lot behind answering the question, how accurate is my GPS receiver? Okay, just finally then, complicated chart, but I just want to talk through it at a high level. So this is, the aim here is to answer the question, do two frequencies give you better accuracy? That's the primary question here. So on the right-hand side, between 1570 and 1580, that's the frequency in megahertz, 1.5 gigahertz roughly. You can see all those signals lined up at 1575.42. That's the GPS L1 frequency. So substantially all single frequency receivers use that frequency and track the coarse acquisition code that we've mainly been talking about. If you look at the top line, we'll just stick on that for now, GPS, you can see two other signals. One with red behind it, that's the GPS L2 signal. And one at a slightly lower frequency, that's the GPS L5 signal. And you can see if you read down the page there on the left-hand side, all of the different GNSS systems have got multiple frequencies. So why might you use multiple frequencies? And what might the impact be? Well, simply put, the key takeaway, in my opinion, is illustrated here. So single frequency on the left, multiple frequencies on the right. And the bar component that's changed the most is the ionosphere. Others will change slightly, but the key thing with multiple frequencies is that you can actually calculate the ionospheric delay rather than just having to model it and kind of accept the error that's not taken account of in the model, which you have to do with single frequency. So you can get a kind of an order of magnitude improvement just by going to dual frequency. Maybe, I hesitate to give a figure, so don't quote me on this, but if you were looking at 5 meters from a single frequency receiver, you could reasonably expect to get down perhaps to 3 meters, or maybe even slightly better with a dual frequency standalone receiver. Now, just by going to dual frequency, you don't automatically improve anything else. There's nothing magic about the second or the third frequencies in terms of the signals. In terms of signals, as far as accuracy is concerned, the accuracy improvement doesn't come from a better signal, is the point I'm trying to make. The accuracy improvement comes from the reduction in the error budget that you can see here. In terms of encrypted signals, I'll just touch on them very briefly. So some of the signals at L1 and other frequencies are encrypted. And Guy, I'm sure, will talk in his talk about jamming and spoofing. Well, encrypted signals are very good against spoofing, and they're more difficult to jam. You saw on the last chart that the width of the signals, the bandwidth, was higher. So you need a more sophisticated jammer to jam them, but they are still susceptible to jamming. You can still wipe them out. There's nothing fundamentally on a different order of magnitude with their power levels. They're still coming from medium Earth orbit satellites, and they're still very low power when they reach the surface of the Earth. So encrypted signals can be more resistant to jamming and spoofing, but it doesn't completely overcome the jamming. It's more the spoofing. So that really concludes my comments here. Just 2 charts with a reflection, perhaps, on the practical implications of what we've just covered. So here's an example of an application indicating that lane-based positioning is the requirement in that white swathe. So could you achieve that single lane positioning using just GNSS? Well, I would argue from what we've just seen that that would be extremely challenging. Would dual frequency help? Well, it wouldn't do any harm, but it doesn't in and of itself create the certainty that single lane accuracy could be achieved. And this example is for positioning here, but it could equally apply to the time error. So I haven't talked much about timing. I've talked more about positioning accuracy. But the time is effectively proportional to the timing accuracy, positioning accuracy, effectively proportional. 1 nanosecond at the speed of light is about 30 centimeters. So if you've got a 5 meter error, that's indicates getting on for 20 nanoseconds in the time domain. Similarly, a 100 meter error would be 300 nanoseconds. So beginning to become significant for certain communication systems. And then, yeah, this one here with the maps. I just wanted to say here that a lot of people focus on getting the best accuracy they possibly can, but then when they put that from their receiver, but when they integrate that into a system or add mapping information, it may be that the resolution of other parts of the system or application are less good than you're achieving from your GNSS system. And here's some example of some roads, which clearly are not exactly correlated to the underlying reality on the surface of the Earth. And this will be discussed more in the next course on the 25th of February. So with that, I will say thank you very much and hand back to Claire.